a delightful opportunity to be here. This is definitely one of the shortest travel trips that I've ever had to give a talk, because my office is just across the street. And this is a familiar space because we ran the Human-Computer Interaction Seminar in here last year. So it's great to be here today. And as Mark said, I'm one of the faculty members in the Mechanical Engineering Department, where I run the SHAPE Lab, but I'm also very much involved with the Stanford Human-Computer Interaction group as well. And so today I'm going to be talking about our work sort of at the intersection between human-computer interaction and robotics and mechatronic systems, and thinking about how can we really enable people to interact in much richer ways. I also have to apologize. I had a hand procedure done earlier today, and basically I thought it was going to be not as painful as it was, and so I'm a little bit more under the weather than normal, so you'll have to believe that this would be even more exciting normally. So speaking of hands, I've long been impressed by the dexterous ability of our hands to allow us to manipulate the world, and certainly having recently had some injury for my wrist, that's become even more clear to me how important our hands are for manipulating things in the world, and really just the amazing complexity of our hands and the way in which we're able to interact so gracefully and dexterously to achieve really skillful manipulations, such as here sculpting in clay, but all of our everyday tasks as well. But to me, what's really exciting about the hand and manipulation is the role of manipulation in terms of our cognition as well. And so physical interaction is very important for not just physical manipulation for the sake of changing the world, but also for us to express our thoughts, as you see me gesturing like this, but also for us to better understand information. So there's been a lot of studies that have looked at how children, when they learn with abaci, for example, or abacus in plural, abaci, that they actually learn math concepts differently and better than if they learn them just on paper and pencil. And so there's something behind this idea of embodied cognition that's actually quite important. And we see that not just in terms of education, but really in terms of very specialized domains as well. So for example, this is a photograph of urban planners and architects. And what we see there is there's this basically rich interplay between the physical models that they're building, space, and the ways in which people want to interact as well. And so physical and spatial form can really help us better understand and solve problems, and very complex ones in the architecture domain, but many other domains as well. And the big kind of reason behind this is that spatial manipulation, as I kind of highlighted before, really aids in spatial cognition. These two things are very tightly coupled together, and one of the great professors that we have had at Stanford, Barbara Tversky, has done a lot of work as well, looking into the role that spatial manipulation plays in our cognition and kind of the evolutionary basis for this as well. So she has a great new book out called Mind in Motion that I highly recommend you take a look at. But in many ways, this is because cognition and perception are very much coupled together through action, and we've evolved over a long period of time to really benefit from the way that we can manipulate the world to better understand it. And these things are tightly coupled together. This is even more important when we think about access to information. And so, for example, these physical representations can be really important for people with different abilities. So here's a picture of a blind student at the Perkins School for the Blind in the Boston area looking, or feeling rather, a double helix model. And this is something that would be very hard for us to explain through words, but by being able to touch, feel, and manipulate it, they can much more easily understand. And this is a tactile model of Berlin's Museum Island. Again, this type of spatial information might be very hard for us to convey through text alone, but by allowing people to directly access it through touch and through our haptic sense, we can much more readily access it. But if we look at the ways in which we traditionally interact with computing and with information, not much has changed since 30 years ago in some ways for the ways in which we interact. And historically, it's been the case that we really haven't been able to leverage our sense of touch in that. And if we look towards, basically newer interfaces for interaction, such as in virtual reality, a lot of times we really get these benefits of spatial interaction, where here I can move around and interact and collaborate with someone else. But when we reach out to feel something or touch something, we're not really receiving any meaningful feedback. And so one of the key questions that I've been interested in, as well as many other people in the field of haptic interfaces, is, what if we could reach out and touch the void? And so during my PhD at the MIT Media Lab, we were really interested in trying to merge between the physical and the digital world and bring that sense of physical touch into the real world. So that if we were, two people working around a workstation, we could look at each other, see each other, and also directly interact with a surface and be able to feel it. And so let me show you what that might look like. So here's a picture of a new type of haptic display. We call it a shape display that we developed at the MIT Media Lab with my advisor, PhD advisor Hiroshi Ishii, and my colleague Daniel Leichtinger, where we could really reach out and sort of sculpt with digital clay. Or we could reach out and new interface elements could appear that have the correct affordances and ergonomics for how we might want to interact. Or we could render different types of 3D models in sort of real time and be able to, again, see them in 3D, but also touch them. So this type of display had been sort of considered before by a number of other researchers, but here we were able to really look at what are these meaningful interaction techniques and start to look at some example applications as well. So this was a project that we worked on with Tony Tane, who is formerly a practicing urban planner. And as I said before, the spatial models that urban planners and architects build are often very important for how they think and consider this space. But they're, basically they would make one set of faux models and then not be able to change anything. And so here we can, in real time, change the models, but also have other simulations that we can load on top of that and be able to, edit, manipulate, and collaboratively work together. So this sort of gives a hint for what this new type of interaction with what we call shape-changing displays might be like. And so when I came to Stanford, I guess now 7-ish years ago or so, I started the Shape Lab to really deeper investigate these types of systems, but also work on some other areas as well. And so in our group, we've been working on new types of haptic displays like the ones that I've shown here. And that's really what I'm going to spend the most of today talking about. But I quickly wanted to mention two other areas that our group has also been working on as well, and that are kind of related to the robotics areas. And so the next area that we've also been thinking about is this notion of ubiquitous robotic interfaces. And really this idea harkens back to someone who maybe some of you know of, but Mark Weiser, who sort of started the field of ubiquitous computing that we really live in today, where there's, in this room around us, many different sensors and many different sensors and displays. There's probably, at least 100, if not 1,000 computers in this room right now. And so the question that we had is sort of what would it be like in the future if we could have actuation and robotics be embedded in our environment as easily as the computing and displays that we have today. And so with my PhD student, who's now a professor at Simon Fraser University, Lawrence Kim, we created this platform of small mobile robots that we could then explore. And again, here we can have them display information like this, but we also looked at ways in which they could be embedded in our environment, like on our desk, move around to display information when we need, but also manipulate things in the environment or go about remotely sensing different things as well. And we think this kind of opens up some interesting opportunities to think about, again, where does this line between robot and environment end? And so that's something that we're also quite interested in and kind of intersects a lot with human-robot interaction. And the last area that we're doing work in is in shape-changing robotics, which is something that Mark highlighted before. And a lot of that has to do with the enabling technologies that we are looking at to make shape-changing displays and also shape-changing robots. And so if you think back to that first example haptic display that I showed that is sort of like a 2.5D surface display, one of the things that we had been thinking about is how might we sort of make full 3D shape-changing displays. This is sort of the holy grail of some of our work in terms of thinking about, oh, how could we actually, feel a whole entire dolphin and actually have it be able to change shape between different surfaces. And so as one of my former PhD students, Zach Hammond, and a collaborator of ours, Nathan Yusevich from Alison Okamura's group, we're trying to think about how might we make this vision a reality. And so we got inspired by basically balloon animals to think about new ways that we might approach this. And the interesting thing about balloon animals, right, is that you start out with something very simple, like essentially an inflated tube, and then we can pinch it at certain points, knot it together, and basically create many different shapes out of the same, simple balloon idea. And so we tried to bring this idea to the field of soft robotics, where we could have basically an inflated beam, and as opposed to relying on pumps to move and actuate different areas, what if we created a pinch point in that beam, and then what if we could move that pinch point around? And then basically what that allows us to do is create some type of system that can really dramatically change shape by putting a robot roller node on that surface and driving it around, and then creating what we call sort of this idea of an isoparametric type of robot, where we have a fixed length of inflated tube, but then we can change kind of the overall basically geometry, even though it has a fixed topology. And so here is one element inside that, but we can place these together through other kinematic connections to create some type of tetrahedral robot that we can then, basically a truss robot that we can then really dramatically change shape. And again, we get these benefits of having this constant volume of air that we don't need to really pump around, but instead using motors to move these pinch points or buckle points around. And so here's an example of what those types of basically truss robots could look like. And so this is a fairly large device, about this size, and it's able to pretty dramatically change shape and move around. And this is all shown in real time. And so it can locomote by basically doing some type of punctuated rolling, change its shape and move around, but it can also go ahead and manipulate objects as well. So it can use the geometry of itself to basically grasp an object and then be able to pick it up and actually do some interesting in-hand manipulation as well. And so we think that this kind of idea of having these large shape-changing truss robots has some interesting applications in terms of thinking about new ways that we could be able to locomote, manipulate, and also use the shape change to afford different types of interaction in the environment. And so we've also done some work to look at the modeling and kinematic control and planning of this as well. So Zach and our group did a lot of work on grasp optimization planning with these types of robot, and we have a collaboration with Matt Schwager looking at decentralized control of these types of systems as well. So I won't go into too many details in that area today. But I just wanted to give you kind of an overview of some of the different things that we're working on in our group. But today I'm really going to focus on these types of shape-changing or haptic displays. And I'm going to start out by talking a little bit about the way in which we approach these problems. And really the way in which we like to think about this in our group is really focusing very deeply on specific applications and needs, working with domain experts in those areas, and then trying to learn more about what are the enabling technologies or the requirements for the enabling technologies to actually make these systems work. And then that kind of feeds back into other applications and needs. And we think this is a kind of a nice paradigm for working on basically new technology to make these things possible. So I wanted to start by talking about two vignettes of specific applications that we've been working on. And the first is in car design, and the second is in making accessible, to sort of highlight some of the challenges in making these systems actually useful. And so many of you might be familiar with car design in general and have seen these types of clay models that basically industrial designers and human factors experts create to create to prototype and test car designs. And so we had been working with Volkswagen, who's trying to transition from making these clay models, which end up costing, something on the order of $100,000 per clay model. So it's very expensive and time-consuming to make those, and moving instead to using virtual reality to prototype and test at scale, especially in terms of working with different stakeholders that they care about, as well as the human factors aspects of like the interior of the car as well. And so what they're trying to do is basically transition from this, very physical style of doing things to now move into the virtual reality systems. But what they found is that, for example, in the case of the interior of the car design, what they call the seating buck and the human-machine interaction, basically they'll be able to load up different car designs in virtual reality, and then they have these very fancy seating bucks to adjust the position and height and steering wheel position to basically create any different kind of car. But then you go and reach out and try to touch the HMI, the human-machine interface part of it, and the dashboard, and basically you again, reach out and touch nothing or touch air. And so one thing that they end up doing is creating these, basically machined or milled foam models that they can then place inside this seating buck to then be able to go ahead and test. But it turns out it takes a long time for them to actually be able to create these foam models. They can't switch something, change things on demand, et cetera. And so we had this idea of what if we could create, interactive seating buck basically simulator where we could create this basically surface that we could change in real time to allow us to explore basically the different HMI interactions and some of the ergonomic issues as well. So we started out working with them on this concept and trying to create a new generation of our tactile displays to be able to do this. So this was led by Alexa Su, and so she created this, basically this is about the smallest that you can do with kind of like low cost off-the-shelf DC actuators. So this has a direct drive between them with the lead screw and many actuators, and we made this modular so you can stack them together. And we also looked at the integration with this as well as in virtual reality. And then we brought it back to our collaborators at Volkswagen, particularly like the industrial designers and the human factor specialists, and they sort of said, oh, hey, this is great. We like the idea, but wouldn't it be great if these could be a lot higher resolution and much cheaper? So in terms of the types of things that they're looking for, we're not still there with this technology. And again, wouldn't it be nice if we could create many of these, not just basically this device here costs something like $6,000 in parts to create. So wouldn't it be nice if we could, basically have this be higher resolution and, basically much larger in scale and lower in cost. So those were some of the feedback that we got, which sort of makes sense in some ways. But then I wanted to highlight another application area that we've been thinking about that also informs some of these other challenges. And so this is in the area of still computer-aided design and this idea of making accessible. And so many of you are probably very familiar with the making movement or maker movement that kind of has gone on over the past 15 or 20 years. And basically, one of the great things about that is that it's really empowered a lot of people and served as a great way to involve more people in STEM education. But that doesn't mean that all people are enabled to do that. And particularly a lot of the tools that we use for making, especially in terms of computer-aided design, are not accessible to people that are blind or visually impaired. And so those people have historically been excluded from those areas. And so while 3D printing can be very helpful in terms of supporting accessible education through the use of creating tactile graphics or other types of materials that blind people can touch and feel, there's really this lack of authoring tools for blind people for them to be able to be the designers and engineers themselves. And so the big problem with these, essentially with these systems that exist for computer-aided design is that they're all based on basically graphical user interfaces where you have to directly manipulate with a mouse and a keyboard as well as the computer screen to be able to select and control many features. And that's really great for people that are sighted, right? We've moved beyond command line interfaces to this direct direct manipulation type of interface. But for someone that's blind and visually impaired, basically the main way that they interact with computers is through different types of screen readers, which basically provide audio feedback. And so how might we think about ways in which they could still be able to use this? So there is some work on using text-based editors for creating geometry. So for example, OpenSCAD is a computed solid geometry modeler where you write basically in a declarative programming language to define the geometry. And there's been some great work at the Dimensions project at the New York Public Library, Chancey Fleet there, in terms of basically using that for people that are blind or visually impaired to write code to then be able to 3D print something. But if you can imagine, and you've used a 3D printer, you know they're not particularly fast. And so basically you write some code, and then while we, people that are sighted would be able to, instantly see the changes that we're making, someone that's blind and visually impaired would have to basically use a 3D printer, wait somewhere between an hour to 10 hours to find out, oh, the change that I made was that exactly what I wanted. And so one of the questions we've been asking is how might dynamic tactile feedback support this type of interaction? And so again, my former PhD student Alexa Su, as well as some members from the blind and visually impaired community in the Bay Area, Sun Kim, who's an access technology specialist at the Vista Center for the Blind, as well as Josh Miele, who is an amazing blind engineer and researcher who's now at Amazon working on accessibility there. We all work together to create and co-design with other blind makers a tool that allows people to use these types of tactile shape displays we've been talking about to in real time have that feedback. So here, basically you're able to write code in OpenSCAD and then in real time be able to touch and feel the geometry and sort of be able to understand what it is. And so one of the questions that we had, and then 3D print the design. So one of the questions we had is, what are the types of interactions that we need to port from these direct manipulation interfaces that are really essential for basically helping blind and visually impaired people understand that? So we did a lot of different co-design sessions to try to understand what these challenges are. And one of the things that's interesting, it turns out that section views are even more important, basically for blind and visually impaired people than for in our, sighted-based CAD systems, because essentially there's no notion of transparency in these types of displays. You're basically just feeling the top surface of the convex hole or whatever. So you can't have any way to display, at least with these displays, this notion of transparency, which we rely on a lot. So we have some, basically promising interactions that we think are possible with this, and compared to like a single point haptic device, we might have less high resolution in terms of the spatial component, but by allowing people to touch it with their whole hands, they're actually much more easily able to understand what it is and the shape. So we think this is a promising direction, but if we look at the types of geometries that the people we were working with are able to create with this type of tactile display, we can see they're quite limited. And so this was a big issue that we found. But there is this real benefit from having this tight coupling of the iteration. And so we think this is a promising direction and very promising in terms of this notion of real-time iterative feedback, and also that people in the blind and visually impaired community really do want to be designers and makers of their own, basically technology. And this type of system can be very empowering for them. But there's still these big issues in terms of resolution. So if we think about a computer display that we might use being very high resolution versus this pin display that I'm showing here, there's a big gap in terms of the resolution and potentially the understandability of that geometry, and then also in terms of access. So if each of those tactile displays that's still low resolution costs upwards of $6,000, that means that many people can't have access to it, as opposed to a $500 laptop that we could use to teach CAD. So across these different application areas, we really saw these big challenges in terms of cost, scale, and resolution, as well as interaction techniques. But I'm not going to talk as much about that today. And so a lot of the work that we've done in the past couple of years has been trying to address or mitigate some of these issues of cost, scale, and resolution. And we've kind of taken two different approaches to try to tackle that in our group. The first is in trying to create new and novel technical solutions, hardware solutions to solve that. And the second area is on kind of what we call kind of perceptual illusions, or using basically perceptual engineering to think about how do we basically use the existing hardware that we have, but maybe use some clever tricks in terms of how we integrate information together to improve the perceived resolution. And so I'm going to talk about both of these areas. So the first area that I'll talk about is on creating higher resolution tactile displays. And this has been kind of a big challenge in the field of haptics for a long time. And there's sort of this big trade-off or dichotomy between people that are trying to make really high bandwidth tactile displays versus people that are trying to make kind of these shape displays or tactile displays that maybe don't need to move as fast or maybe don't need to move at all. And how do we find this balance between the two? And so one of my former PhD students, Kai Zhang, started to think about ways in which we could really try to push the resolution if we trade off on that bandwidth side of things. And so if we think about this design space or list of design requirements for like the ideal or ultimate tactile display, there's a lot of different things that we might consider, one of which is like, what is the necessary resolution? And so we can look to the haptics and psychophysics literature for some intuition around that. Basically, if we think about, just statically touching a shape, something like that, we need to be in that 1 or 1.25 millimeter range for us to be able to not really be able to feel individual pins. So you could think about this idea of the retina display that you might be familiar with from Apple's marketing, where if you look at an iPhone today, you can't see where one pixel ends and the next begins. Basically, this 2-point discrimination threshold is kind of the same concept, and so we want to be in that 1 to 1.25 millimeter range. But that's, I would say, a very generous, basically ballpark estimate, because actually, if you start to move your finger, then you can basically feel, down to, tens of microns or below. So you can feel, a single hair very easily. But that's relying much more on your, basically cutaneous information from vibration and essentially texture information. But if we just think about gross shape, this 1.25 millimeters gets us pretty close. So as I said, people have been trying to work on this problem for a long time, and there's a lot of different approaches in our own work. We've used basically mechanical linear actuators and also different types of pneumatic actuators, which have, again, challenges in terms of scaling these down, as well as basically the high cost of the actuators and being able to scale those together. Other people have created like electromagnetic tactile displays, but in general, those have some challenges as you scale them down because the electromagnetic fields start to bleed in with each other. So there's some interesting work from Juan Zarate and Herbert Shea in terms of thinking about electromagnetic shielding for this, but they're still kind of on the centimeter scale type of size, or other people using electroactive polymers. And again, all of these are really thinking about this idea of, how do we make a really fast or high bandwidth tactile display? And so the intuition that Kai had was, okay, let's not focus on the high bandwidth aspect, but instead, what if we had something that's much more like e-ink, where, we're not changing it very frequently, we're going to kind of refresh the whole thing. How can we instead have maybe clutches or brakes that we could engage or lock when we need them to, but then have one global actuator that might change everything? And so by trading off on this high bandwidth or the temporal domain or frequency domain, and instead focusing on the spatial, what might we be able to do? And so the technology that we sort of came to in terms of a good trade-off between this sort of high force density in terms of braking or clutching, and then also the scalability is electrostatic adhesion. And so many of you are probably familiar with the electrostatic effect, where basically you have a balloon, you rub it on your hair, and it sticks to your head. And so this has long been used in different industries, for example, in like wafer chucking and the in the semiconductor industry and paper handling and other things. And then over the past 15 or so years, it's really come into vogue in the robotics community as well. So probably many of you are familiar with it, but and also very commonly used in the MEMS scale devices as well. And so basically, we started to think about how can we make these millimeter scale, basically high force density clutches, and what are the different techniques that we might need to use to do that. And we think that this is a promising technology for this type of refreshable display. And so basically here we can see kind of an example of one of these displays where we have essentially a dielectric thin film that we've then patterned with these interdigitated electrodes that are on the order of basically a millimeter across, and then we can basically turn on an electric field that then basically induces some charge on these brass or different types of metal pins and then locks them into place. What does this actually look like in action? Okay, great. Yeah. Yeah. So basically, we can raise up, so it's a refreshable display. So essentially, now we unlock all the pins, we raise them up, and then as we move it down, we lock them into place. And so the electrostatic clutches can turn on and off very quickly, giving us very high precision in terms of linear positioning, and are relatively high force compared to their size. So again, the basic operating principle is that we have this interdigitated electrode that's serving as this clutch that's on one side of a high dielectric constant thin film, and then on the other side there's a pin, and basically we induce opposite charge on the pin, and that basically creates this electrostatic force. And so a kind of very simple model of how this electrostatic force works is very similar to the parallel plate capacitor equation, where essentially the things that matter are essentially the dielectric constant of the thin film, the contact area between the metal pin and the dielectric film and the electrodes on the other side, the voltage, as well as the film thickness. And so historically, in kind of robotics and other applications, people have really pushed on the voltage as the thing to kind of improve the actuation force. Here we have some challenges in doing that because one, we're dealing with people, and basically some of these very high 10 kilovolt types of range, a very small amount of current can actually be not very good for people. So that's one issue. And then the other issue is we want to have, not just one of these actuators, we want to have tens of thousands of these actuators. And so how can we have, very small and low cost transistors that allow us to, scale this in terms of production? And so we ended up trying to push more on the thinness and also the high dielectric constant as things that we could push on as opposed to the voltage because of those two constraints. So this is kind of basically what the actual device looks like when we fabricate these and using the UV laser cutter that Mark's lab, or actually Allison Okamura's lab, well, I forget where it is now, but basically between Mark and Allison, exactly, shared facility, which is great. Basically, that allows us to very easily fabricate these and test out different patterns. And so we use PVDF, which is a high dielectric constant thin film, and a very small sheet of it. And then we have gold that's sputtered directly on it, or some other aluminum, for example. And then we laser ablate off the parts that we don't want. So the actuation principle is very simple in terms of we have these clutches, and then we lower down the platform, lock. When the pins get to the right place, we turn on the clutch, and then we create the whole pattern. And then when we want to erase it or refresh it, we just turn them off and then move the pin up and down. And so we can get, again, very high spatial accuracy in terms of the, basically the linear positioning of the height, because we can turn on and off the clutches in about, on the order of 10 milliseconds or so. Which allows us to have pretty high spatial resolution. We've also done a lot of work on quasi-static loading as well, and unfortunately, basically other people as well. So, for example, Steve Collins' lab has done a lot of work on these electrostatic types of clutches, and also found that basically the back of the envelope calculations don't really end up matching very well with performance because of the effective contact area. And so we've done a lot of work also on data-driven modeling for this. But basically, we think these clutches, on the order of 50 to 100 grams of force for the areas that we're looking at, which is not that much force. But if we think about the contact force that's necessary as you're exploring something, that's on the order of 51 grams of force, and that would likely be spread across multiple pins as well. So we think we're in the right ballpark for this, and my current student, Ahad, who's there now, is trying to work on improving the performance and thinking about other things. So we've done some user testing as well to explore how well these tactile displays work, and it seems like it's a promising direction and seems to be working very well. So we think this, basically these electrostatic pin displays are kind of a promising approach to really pushing the resolution and low-cost aspects of these types of refreshable tactile displays. So that's something that we're quite excited about, and we've been able to achieve sort of this 1.5 or 1.7 millimeter pitch as well. One of the challenges with these types of displays, though, is that they end up creating these very discrete types of shapes, right? And so it's possible that we might want to have more continuous shapes that could be approximated better with some other method. And also, maybe there's a way to do that where we trade off, basically, and basically are able to have, basically more continuous shapes with fewer number of actuators. And so Ahad, who recently had a paper that was accepted to ICRA, that's on thinking about how might we make these basically more continuous shape displays, and what are techniques we could use to sort of have sort of a monolithic manufacturing process where we can kind of create these in one go. And so Ahad has been working on thinking about kind of the combination of electrostatic and electroadhesive actuation with auxetic materials to be able to create basically these shape-changing continuous displays where we're able to vary the curvature of them by locking individual cells in an auxetic grid or an auxetic network. And so here's an example of that shown here. And so basically the idea is that we have work in auxetic skins where we can basically have these different patterns that can expand basically differently based upon how much strain there is in the system. And what we're doing is then locking some of these cells in this auxetic pattern. And what that does is it means that there's going to be very different local strain concentrations that end up, as you inflate this surface, being able to create different geometries. And so basically there's been exciting work in the computer graphics field as well as in other areas on basically being able to computationally design these auxetic patterns so that you can then create some arbitrary geometry that's beyond sort of like what a developable surface could be. And our kind of contribution here is to think about, as opposed to being able to essentially pre-plan and create a custom auxetic pattern that could create some given shape, could we essentially create a smart skin where we can change that local amount that each cell can open and close in real time or at runtime. And so basically the way that we do that is by having each auxetic cell essentially be electrostatic brake or clutch that can basically either open or close depending on how much voltage we're applying across them. And so what this means is that we want to have essentially an auxetic pattern with a very large surface area because, as I said before, the electrostatic force is basically proportional to the amount of surface area that we have. And so essentially we've looked at different patterns, but this one here again has a very large surface area. And so what we end up doing is taking two of these sheets and then rotating them off phase so that basically essentially there's a lot of overlap between them, and we can essentially lock which parts will expand and which parts won't. So here you get an idea of what that single cell might look like. And so we have two, so here you can see these these sets expanding and contracting. And so essentially we can, as we pull on them or inflate them, they're opening up and closing, and we can basically turn on the electrostatic adhesion to lock them and allow them to not open up, which means that basically there's less displacement and less strain in the system. So we've looked at different types of combinations of layers and different materials as well, and are looking at, basically how do we then make this into this monolithic system. So again, there's these two sheets that are on top of each other, and then basically we create them out of this flexible printed circuit board. And so that's really nice because we can just go ahead and fabricate that using off-the-shelf printed circuit board techniques. And then we have one sheet that's in this orientation, then a dielectric thin film in between, and then the other flex PCB that's on the next side as well. So then that's what this sort of 2D surface here looks like, and here we're engaging and locking between them, and you can see some of them start to fail as well. I guess that was the unlocked one. Here, this region below is locked and above is unlocked, you can sort of see. And then here's the locked region, and at a certain point it'll start to fail as well. And so basically we can, again, computationally control which of those areas we want to be locked and unlocked, and that allows us to create these different shapes. And then we have an inflated bladder that's underneath it that we can then basically inflate, and that will then create this global shape change. And so here's kind of an example of this 100% locked, which sort of creates this, basically a very uniform shape. And then now we're locking less and less of the display to create different curvatures, if you can see like that. So we think, again, this is kind of a promising approach. We're still looking for basically auxetic patterns where we can have higher amount of strain and more basically curvature that we can create then. But we think this, again, has some benefits in terms of being able to really create and manufacture this very quickly. A related project that was kind of in the early stages is on kind of connecting this idea of these continuous shape displays with some of the work that I showed at the beginning on these shape-changing robots, where basically we want to have these elastic grid shells. So if you think about it in computer graphics, we often have like NURBS surfaces, which are kind of combinations of these different splines that are connected to each other. What if we do that in the real world? And so basically Sophia Weitzner and Winsam Law in our group are trying to create these robotic elastic grid shells that can then, again, change their geometry in real time. This is a small 1x1 prototype, but here you can see we locked one part of it, and then we're able to inject more material into it and create this curvature there. And so this is what we're kind of aiming to do on the left, is create these, basically interconnected grid shells so where you can in real time change their surface. So these are some of the things we've been doing in our group to think about, how can we push forward and make these higher resolution, surface displays. And I think we've had some great promise in looking at electrostatic adhesion, as well as kind of new approaches to making more continuous surface displays. But I think it's really clear to us, and probably you as well, that the hardware will really never perfectly render the real world, right? The real world is so rich and very complex. And so I think there's this big gap between that. But the interesting thing is that our perception is also imperfect as well. And so maybe we don't need to have perfect hardware when we're considering these types of displays. And so the last part of my talk, I want to talk about some of the work we're doing in terms of using Visio-haptic illusions to improve the perceived performance of these types of tactile displays or other types of shape displays. So the first is work from my former PhD student Parastu Abtahi, who's now starting at Princeton University next year, that's looking at this same problem of how we might use the fact that our visual perception is often dominates our haptic perception. And so one way to illustrate this is, basically our proprioceptive system is not very good. And so if I am able to basically touch my fingers together in front of my face, I'm actually often using my visual system to really help me with that. But if I try to do it above my head, I can sometimes get it, but you'll find that it's not as accurate. And so again, that's because of all of the kind of errors along the line in terms of our different joints and the different mechanoreceptors that we have. But our proprioceptive system has more noise and error than our visual system, and therefore our brains, when we're thinking about integrating this multisensory integrating this multisensory information tend to rely on our visual system. And so as I mentioned before, there's many of these limitations of these shape displays that I talked about in terms of low spatial resolution, limited display size, or low actuation speed. And the intuition or insight that Parastu had was, oh, how can we leverage this fact that our proprioceptive system isn't very good to sort of increase the perceived resolution? And this really kind of essentially builds on a technique from the field of virtual reality that's called redirected touch. Some of you might be familiar with the idea of redirected walking, where again we can kind of steer people in virtual reality by having some slight offset between where you are in the real world and where you see yourself or where you see your hand in the virtual scene. And so what we can do is essentially apply some small virtual offset as I'm reaching that basically makes it seem like my hand as I move straight is moving to the left, and my basically visual motor system will basically compensate for that and make my hand move to the right in the real world to basically compensate for that bias or shift to the left. And so we can basically computationally steer where a person's hand is going by applying these offsets in the virtual world. And by leveraging that redirected touch effect, we're able to address some of these different aspects of low spatial resolution and low actuation speed. And so I'll talk about some of the ways in which we're doing that here. Using angle redirection, scaling up, and vertical redirection as well. So you might be familiar with this idea of anti-aliasing, or the aliasing effect that happens when we look at graphical display. This aliasing effect is actually also very pronounced in these tactile displays as well. And so one way that we were trying to mitigate this low resolution is by trying to essentially get rid of this aliasing that happens when you display a diagonal line. And so if we see here, as we move along the surface here, basically we have this kind of, again, aliasing effect that you can feel these bumps as well. And so what if instead we could redirect you so that you're moving along a straight line, which is doesn't have that aliasing problem, but in the virtual world, you think you're moving along this diagonal line. And so again, by applying this slight offset between where your hand is in the real world and where it is in the virtual scene, we can make you touch different areas of the display and not be able to realize it or perceive it. In terms of the overall resolution of the device, we can think about the number of pixels or taxels that you're in contact with as you move over a surface, right? And so one of the challenges, right, is if we have a small object that we're rendering on a tactile display of a fixed resolution, then you're not going to encounter that many taxels as you move along the surface. So again, what if we could change this, essentially control the display ratio, or utilize this offset between where my real hand is and my virtual hand is, and in the virtual scene render a small object, but in the real world render a larger object of the same version, and we can render it in higher resolution. So again, we can change the ratio between where I'm interacting in the real world, where I'm interacting in the virtual world, and leverage that to improve the perceived resolution. And we've done this also for things like extending the height of the display, the workspace limitations of it, and other things like that as well. So here you can see as I'm moving up, I have some fixed amount of range that I can move up. And then here, we're able to, again, offset where you think your hand is in the virtual scene. And so you can think that basically the tactile display has larger pins than we can actually create with these displays. We've run a lot of psychophysical studies to find what these thresholds are, and also find that when we display these underneath basically when we display an offset underneath that threshold, essentially people perceive it as being higher resolution without noticing that it's there. But we've also found some interesting effects in the difference between active versus passive touch, where in the active touch conditions, that's where you're moving your hand as well. So for example, in that angle redirection, we can't offset people's hands as much as we can in the passive touch condition, where, for example, the motor is moving your hand, where we can offset people more. And so again, that has to do with kind of the forward model that people have in their sensory motor system in terms of basically my predictions of where my hand might be. And so I'm more willing to allow things to have noise and there to be more air when I'm being moved versus I'm moving myself as well. So we've looked at ways in which we can leverage this to create different types of applications, such as improving the resolution or again, increasing the vertical redirection as well. But as you can see from those types of systems, these illusions really only work in this small area of the display. And so another set of work that we've been doing is trying to improve the kind of scalability of how we might apply these to a much larger area and create essentially what are called encountered type haptic displays that might operate over a larger region. So we put these types of haptic displays, tactile displays, on a robotic arm, and then when we reach out, the robotic device can be there in time. But one of the challenges with this type of approach of encountered type haptic devices is that oftentimes the device has some limitations as well, right? So the device may arrive late, or it might be out of the workspace of that robotic system. So I want to touch something up here, but the robot is only down there. And so again, there's a number of challenges with these encountered type haptic devices in terms of different reachability issues that lead to these uncertain spatial discrepancies, which really kind of affect people's perceived performance of these devices. So we've done a few things in this area to improve essentially the ability for these devices to work by essentially redirecting your hand to the reachable area of the robotic system. Great. Okay, great. So anyway, basically we can do some cool things in terms of this redirection to guide people into different people's space. And we've also done some interesting work on trying to apply basically model predictive control to basically run this in real time to improve the perceived performance using a model of human reaching and sensory integration. So I think that I'll conclude there with just one short statement, if I can find it, which is that we started out this work really thinking about how real does haptics need to be? And I think where our group is going is really trying to think more about how real does haptics need to seem, and really trying to leverage this sensory motor control perspective to optimize both the hardware and the software together. So I'd like to thank my PhD students and postdocs in my lab that contribute to this work, as well as our funding sources. And I guess I'd be happy to answer any questions. Yeah, I thought it was till 1:30, so my apologies on that, Mark. Yeah, so thanks so much.